Hello, I'm SA, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
A computational monolith of the early 1980s, Hitachi Hitachi 2KH, represented the pinnacle of Japanese mainframe power. Its central processing units, cooled by elaborate water circulation systems, hummed with a purpose that would seem almost mystical to an outside observer. The machine, capable of executing millions of instructions per second, was dedicating its immense resources, its precious memory, its costly processing cycles to a singular, relentless task. The objective was the expansion of a number known to school children and scholars like the constant pi. This pursuit, however, was far from a simple exercise in arithmetic. It was a brutal confrontation with the fundamental architectural limits of digital computation itself, a crucible where abstract mathematical theory was forged against the unyielding constraints of hardware. At the heart of this crucible stood the figure of Yasumasa Kanada, a professor at the University of Tokyo whose intellectual disposition was uniquely suited to this grand challenge. The central difficulty resided deep within the machine's design philosophy. Computers of that era, powerful as they were for tasks in finance, engineering, or database management, were constructed around the principle of fixed precision arithmetic. Their internal logic handled numbers represented by a finite number of bits, typically 32 or 64 in what we call floating point formats. These formats are marvels of efficiency for most scientific calculations, offering a compromise between range and precision. For Kanada's ambition, they were wholly inadequate. His goal of computing millions and eventually billions of digits of pi required what is known as arbitrary-precision arithmetic. This is the capacity to represent and manipulate a number whose size is limited only by the available memory of the computer. A number with 2 million decimal places is an entity that a standard processor simply has no native concept of. It cannot be loaded into a single register or handled by a single machine instruction. Kanada's initial, formidable task was therefore one of pure creation. He had to build a complete computational ecosystem from the ground up, a software layer that would effectively teach the Hitachi supercomputer how to think about mathematics on a scale its designers had never envisioned. This involved writing bespoke software systems for multi-precision operations. Imagine a number stretching across thousands of memory addresses, stored as a vast array of smaller integers. To add two such colossal numbers, one needs a program that mimics the grade school column-by-column addition method, complete with carrying over digits, but executed with flawless, high-speed logic. Multiplication was an exponentially more complex problem, demanding algorithms of immense sophistication to avoid a crippling slowdown as the number of digits grew. This work forced Kanada to become a master of the machine at its most elemental level. He delved into the specifics of the Hitachi 200H's architecture, studying its instruction set, its memory addressing schemes, and the precise clock cycle cost of every operation. His code was a model of optimization, tailored to extract every last ounce of performance from that specific hardware. He was, in essence, a composer writing a symphony for a single, unique instrument, knowing its every timbre and limitation. His approach was a powerful synthesis of the elements of number theory, meeting the brute force reality of machine code. This intense focus on implementation was propelled by a crucial theoretical breakthrough that had occurred a few years prior. For centuries, the calculation of pi had been dominated by formulas involving the arctangent function, most famous being John Machen's formula from 187 times 6. While effective, these formulas exhibit linear convergence, meaning the number of correct digits produced is roughly proportional to the number of terms calculated. Progress was slow and laborious. Then, in 1976, Eugene Salamin, working at Stanford, and Richard Brent at the Australian National University, independently discovered a new type of algorithm. Their method, now known as the Salamin-Brent algorithm, was based on the arithmetic geometric mean, a concept explored by the great Carl Friedrich Gauss. The profound importance of this discovery lay in its convergence property. The Salamin-Brent algorithm is quadratically convergent. In simplified terms, this means that each iteration of the algorithm roughly doubles the number of correct digits. The leap in efficiency was staggering. It was like trading a staircase for an elevator. Suddenly, calculating millions of digits became a feasible, albeit still monstrously difficult, undertaking. Salamin and Brent had provided the theoretical key, a beautiful and powerful piece of mathematics. It was Kanada who possessed the rare combination of skills in numerical analysis and systems programming to turn that key in the lock of a real-world supercomputer. He saw the potential of their abstract formula and understood precisely what it would take to translate its mathematical steps into an optimized sequence of machine operations. His initial forays culminated in a landmark achievement in 1981. Using his custom-built arithmetic software on the Hitachi 200H, Kanada and his team computed pi to 2,097,552 digits. At the time, this was a significant calculation, though it fell short of the standing world record. Its true importance, however, was as a proof of concept. It was a definitive demonstration that his methodology, the tight integration of quadratically convergent algorithm with hardware-specific, low-level software optimization, was sound. He had successfully built the engine and taken it for its first serious run. The result validated years of painstaking work in software development and served as the foundation for all his future endeavors. It established his laboratory at the University of Tokyo as a global center for high-performance computation and announced the arrival of a new, formidable competitor in the esoteric race for the digits of pi. This early triumph was about establishing a process, a system of inquiry that treated the supercomputer as an integral part of the mathematical experiment, forever linking the abstract beauty of a number with the physical power of the machine built to explore it. The stage was now set for a far grander assault on the frontiers of calculation. The assault on pi's infinite expanse demanded a new philosophy of computation. With a foundational methodology established, Yasumasa Kanada and his team at the University of Tokyo turned their attention from achieving millions of digits to conquering billions and eventually trillions. This escalation represented a profound shift in scale. The challenge was one of exponential complexity, where each successive world record required an almost complete rethinking of algorithmic efficiency, hardware utilization, and the very concept of computational reliability. Pushing the boundary of pi became a proxy for pushing the absolute limits of what was technologically possible. A high-stakes endeavor where the primary adversary was a tyranny of large numbers. At the core of this campaign lay a deliberate and masterful selection of mathematical tools. The era of relying on slowly converging arctangent formulas, like Machin's, was over for anyone serious about setting records. Kanada's team embraced a new generation of algorithms characterized by their astonishingly rapid convergence. The first of these was the Gauss-Legendre algorithm, an iterative method with quadratic convergence. This property is transformative. With each step of the algorithm, the number of correct digits approximately doubles. It is the mathematical equivalent of climbing a mountain in exponentially larger strides. The algorithm itself is an elegant dance between the arithmetic mean and the geometric mean of two numbers, a process that converges with breathtaking speed toward a value from which pi can be extracted. This quadratic convergence, while a massive improvement, was soon complemented by an even more potent family of formulas. The algorithms developed by the Canadian brothers Jonathan and Peter Borwein, working with David Bailey, they discovered iterative schemes that exhibited quartic convergence, meaning the number of correct digits quadruples with each pass. Kanada's team was among the very first to recognize the profound practical implications of these theoretical breakthroughs. They seized upon the Borwein's quartic algorithm, a formula of beautiful, almost startling simplicity given its power. Its implementation became a cornerstone of their most ambitious record attempts. The adoption of these algorithms signaled a strategic choice to build their computational empire upon the most advanced theoretical bedrock available, linking pure mathematics directly to the bleeding edge of computer science. The choice of algorithm, however, was merely the blueprint. The true engine of Kanada's success was his team's unparalleled mastery of the fundamental operation underlying all high-precision arithmetic, multiplication. When multiplying two numbers with a billion digits each, a naive grade school approach would require a number of operations proportional to the number of digits squared, a figure so vast it would render any computation impossible. The solution lay in the Fast Fourier Transform, or FFT. This powerful algorithm, originally developed for signal processing, allows for the multiplication of two n-digit numbers in time proportional to n times the logarithm of n. For the scales at which Kanada operated, this difference was astronomical. It was the difference between a calculation taking centuries and one taking weeks. Kanada's unique contribution was the development of highly optimized, parallelized FFT-based multiplication routines, painstakingly coded in low-level languages to extract every ounce of performance from the specific supercomputer architecture at hand. His software was a bespoke creation tailored to the memory layout, cache behavior, and communication pathways of the Hitachi supercomputers he employed. This created a true symbiosis between algorithm and hardware, a tightly coupled system where the mathematical logic and the physical machine were inseparable components of a single computational instrument. This synthesis of theory, software, and hardware reached its zenith in 2002 on a 64-node Hitachi SR/SP supercomputer, a colossal machine for its time. Kanada's team calculated pi to 1.24 trillion digits, shattering their own previous record. This monumental effort consumed over 600 hours of dedicated processing time. The computation utilized one of the Borwein brothers' quartic algorithms as a primary engine. The massive multiplication steps, involving numbers with trillions of binary digits, were handled by his custom-built, massively parallel FFT library. The achievement was a landmark in the history of high-performance computing, a demonstration of what could be accomplished when every element of the computational stack, from abstract number theory down to the flow of bits through silicon, was orchestrated in perfect harmony. A result of this magnitude introduces a daunting epistemological problem: how can one be certain of its correctness? With no existing answer key, verification becomes as challenging as the initial computation. Kanada's solution was one of intellectual rigor and elegance. His team would perform the entire calculation twice, using two completely different algorithms. For instance, a primary run using the Borwein quartic algorithm would be verified by a secondary, independent computation using the quadratically convergent Gauss-Legendre algorithm. The probability of two distinct, complex algorithms producing the exact same trillion-digit sequence due to a shared, systematic error is infinitesimally small. When the final digits of both computations matched perfectly, it provided an exceptionally high degree of confidence in the result. This dual algorithm strategy became the gold standard for validating high-precision computations, a testament to a scientific mindset that valued certainty as much as speed. The enduring impact of Kanada's pi computations extends far beyond the realm of numerical record-keeping. His published methods and results became a de facto benchmark for the entire field of high-performance computing. Hardware vendors and computer architects used his pi calculating programs to stress-test new supercomputer designs as the task pushed every subsystem processors, memory, storage, and interconnects to its absolute limit. Furthermore, his work provided a direct intellectual lineage to the next generation of computational mathematicians. Alexander Yi, the creator of Y-Cruncher, the software that now dominates modern pi computations on distributed and personal systems, explicitly studied Kanada's papers on FFT-based multiplication and large number arithmetic. Yi built upon the foundational techniques that Kanada's team had perfected in the supercomputer era, adapting and refining them for the multi-core architectures of the 21st century. In this way, the insights forged in the pursuit of a single transcendental number propagated outward, shaping the tools and methods used across computational science. The conquest of pi, for Kanada, was the ultimate validation of a powerful, integrated computational paradigm, one whose principles were ready to be unleashed upon other fundamental constants of the mathematical universe. This validated paradigm, forged in the crucible of pi, immediately posed a compelling new question for Yasumasa Kanada and his team at the University of Tokyo. The intricate machinery of high-precision arithmetic, meticulously optimized for the unique geometric and algebraic properties of a single transcendental number, now stood as a monumental achievement. The question was one of scope and universality. Could this powerful engine, with its fast Fourier transform-based multiplication and its mastery of iterative algorithms, transcend its original purpose? Could its principles be generalized to attack the distinct computational challenges presented by other fundamental constants, each with its own mathematical personality, its own series, its own rate of convergence? The quest for pi had yielded a magnificent key. The task ahead was to discover how many other doors in the mathematical cosmos it might unlock. The foundation of this potential universality lay in the core architecture of Kanada's computational system. The true breakthrough was the creation of a highly efficient, Arbitrary-Precision Arithmetic Library, the FFT-based multiplication algorithm, which transforms the problem of multiplying two immense numbers into a sequence of transforms and element-wise products, is agnostic to the source of those numbers, whether they represent partial sums for pi, terms in the series for Euler's number, or iterates in a rote-finding algorithm. The arithmetic engine performs its function with the same breathtaking efficiency. This realization shifted the problem. The challenge became one of translation, identifying or deriving suitable mathematical formulas for other constants, and then skillfully implementing them to feed into this powerful, general-purpose arithmetic core. Each new constant represented a fresh intellectual puzzle, requiring a deep dive into its specific mathematical literature to find the most computationally tractable representation. An early and logical target for this expansion was Euler's number, E. Mathematically, E is defined by one of the most elegant series in all of mathematics, the summation from n equals 0 to infinity of 1 divided by n factorial. This structure is quite different from the rapidly converging Borwein or Chernovsky algorithms used for pi. A naive summation would be hopelessly slow. Kanada's team approached this by employing sophisticated algorithmic refinements like the binary splitting method. This technique cleverly groups terms of the series, allowing the computation to be structured as a recursive process. At each step, it calculates integer numerators and denominators for large blocks of the series, performing a single, high-precision division only at the very end. This minimized the number of computationally expensive division operations, the Achilles heel of high-precision arithmetic. The successful computation of e to millions and then billions of digits was a crucial proof of concept. It demonstrated that the underlying library was flexible enough to accommodate different algorithmic strategies, moving from the arithmetic geometric mean iterations of pi to the optimized series summation required for e. The principle of generalization extended even to seemingly elementary operations, such as the calculation of square roots. Elevated to an extraordinary scale, computing the square root of 2 to billions of digits, for instance, becomes a formidable task. Kanada's approach here drew from the deep well of numerical analysis, employing Newton's method, a classic root-finding algorithm. To find the square root of a number, say n, one seeks the root of the function f of x equals x squared minus n. Newton's method provides a powerful iterative formula of the next approximation, x sub n plus 1, is equal to the current approximation, x sub n, minus the quantity f of x sub n divided by its derivative, f prime of x sub n. The beauty of this method lies in its quadratic convergence. With each iteration, the number of correct digits roughly doubles. When coupled with Kanada's high-precision arithmetic engine, this ancient algorithm transformed into a computational powerhouse. The challenge was immense, demanding perfect management of precision through each iterative step to prevent the accumulation of catastrophic errors. This achievement showcased the system's capacity to handle iterative schemes far different from the AGM, proving its utility for a broad class of problems in numerical analysis. Perhaps the most compelling demonstration of the program's power as a tool for mathematical exploration came with its application to Perry's constant, also known as zeta of 3, defined as the sum of the reciprocals of the cubes of the positive integers, or the summation from n equals 1 to infinity of 1 over n cubed. This constant occupies a mysterious place in number theory. For centuries, the nature of the zeta function evaluated at odd integers was a source of profound speculation. Then, in 1978, a celebrated and initially startling proof, the French mathematician Roger Perry established that zeta of 3 is irrational. Perry's work, which directly influenced a new generation of number theorists, left open deeper questions, chief among them whether the constant is transcendental. Here, Kanada's work entered the realm of experimental mathematics. The standard defining series for zeta of 3 converges far too slowly for practical high-precision computation. A direct attack would be futile. Instead, Kanada and his collaborators, including his student Daisuke Takahashi, scoured the mathematical literature for more advanced, rapidly converging series for the constant. They implemented one such formula, likely one of the sophisticated hypergeometric series representations discovered in the wake of Perry's proof. The computation of the binary digits of zeta of 3 to over 1 billion places was a landmark achievement. It was a calculation performed with a clear scientific purpose to create a massive data set for number theorists to analyze. Mathematicians could now perform statistical tests on this vast sequence of digits, searching for non-random patterns, periodicities, or other subtle structures. The absence of such patterns would lend weight to the conjecture that zeta of 3, like pi, is a normal number of property consistent with transcendence. This work exemplified a new symbiosis between computation and pure theory. The computational engine, once a tool for setting records, had become a sophisticated instrument for generating mathematical evidence, allowing theoretical conjectures to be probed and explored on an unprecedented scale. Through these very achievements, the computational paradigm developed by Yasumasa Kanada demonstrated its profound versatility. The intellectual framework built for a single, iconic constant proved to be a robust and adaptable platform for numerical inquiry across a wide spectrum of mathematics. It established a powerful methodology, combined a deep understanding of the mathematical properties of the target constant with a state-of-the-art, arbitrary-precision arithmetic library. This combination turned the act of computation into a form of scientific exploration, creating a feedback loop where theoretical insights from number theory guided the choice of algorithms, and the resulting computational data fueled new theoretical investigations. The immense computational power, once focused inward on the digits of pi, was now directed outward, illuminating the fine structure of the mathematical universe. This very power, capable of pushing a supercomputer to its operational boundaries for days on end, also suggested another profoundly practical application: its use as the ultimate diagnostic tool for the health, stability, and performance of the machines themselves. The immense computational stress inherent in calculating trillions of digits possessed a utility that extended far beyond number theory. The very act of pushing a machine to its absolute operational limits for days, even weeks, transformed the esoteric quest for pi into a profoundly practical diagnostic crucible. In the burgeoning era of supercomputing during the 1980s and 1990s, as architectures grew dizzyingly complex with vector processors and nascent parallelism, a fundamental anxiety haunted the field. A machine that delivered a brilliant, world record speed while producing a subtly incorrect answer was worse than a slow machine. It was an engine of deception, capable of invalidating entire fields of scientific simulation built upon its output. The challenge was one of trust. The solution required a figure who could bridge the worlds of abstract mathematical truth and the brutal, physical reality of silicon, heat, and electricity. Yasumasa Kanada, through his relentless pursuit of transcendental numbers, became one of the world's foremost architects of that trust. His pi computations functioned as the ultimate gauntlet for a high-performance computing system, a holistic trial by fire that few synthetic benchmarks could ever replicate. A successful run was a certificate of integrity for the entire technological stack. The process began with a central processing units, subjecting their floating point arithmetic logic units to a relentless, sustained barrage of calculations, probing for the kind of subtle, intermittent errors that might only manifest under extreme thermal load or after billions of operations. Simultaneously, the algorithms employed, particularly the Fast Fourier Transform at the heart of the multiplication routines, placed an enormous strain on the memory subsystem. The constant, high-velocity shuttling of massive arrays of numbers between the main memory and the CPU caches tested the system's bandwidth, latency, and data coherence with a ferocity that few other applications could match. A single flipped bit, a momentary hiccup in the memory controller, would cascade into catastrophic error, rendering the entire multi-week computation worthless. Furthermore, the scale of these calculations saturated the input and output channels of the machine. Intermediate results, often spanning hundreds of gigabytes or even terabytes of data, had to be written to and read from disk storage reliably and efficiently. This process served as an exhaustive stress test of the storage controllers, the physical disk arrays, and the file system's ability to manage colossal files without corruption. Finally, the entire software environment, from the operating system's kernel scheduler to the C compiler's optimization, heuristics, and Kanada's own meticulously crafted arbitrary-precision arithmetic libraries, had to perform in perfect, unwavering concert. A pi calculation that completed and, crucially, verified against a previously computed sequence of digits was an unambiguous testament to the stability and correctness of the entire integrated system. It was a real-world workload of the most demanding kind, and its successful execution provided a level of confidence that a simple pass-fail diagnostic could never offer. This deep, practical understanding of machine limits positioned Kanada perfectly to engage with the era's most significant effort in standardized performance measurement, the LINPACK benchmark, as American firms like Cray Research and Japanese giants like Hitachi, Fujitsu, and NEC vied for computational supremacy. A high-performance computing community required a common language, a standardized yardstick to compare their increasingly divergent architectures. LINPACK provided that language. Developed by a team, including Jack Donder at Argonne National Laboratory, the benchmark measures the performance of a computer in solving a dense system of linear equations, a problem typically expressed in matrix form as a times x equals b. The result is reported in a now famous metric flops, or floating point operations per second. The choice of this particular mathematical task was profoundly insightful. Dense linear algebra is a computational bedrock of a vast swath of scientific and engineering disciplines. Its routines are fundamental to everything from quantum chemistry simulations and weather forecasting models to finite element analysis in structural engineering and fluid dynamics calculations for aerospace design. A machine's proficiency in solving such a system is a powerful proxy for its utility across the scientific domain. Kanada and his research group at the University of Tokyo became world-leading specialists in implementing and optimizing the LINPACK benchmark, particularly for the unique vector processing architectures of Japanese supercomputers. It would meticulously hand-tune the Fortran code, reordering loops and managing data layout to ensure that the machine's vector pipelines were constantly fed with data, maximizing computational throughput. This painstaking work was instrumental in demonstrating the formidable power of systems like the Hitachi SA-20/80, allowing them to achieve and document performance figures that secured them top rankings on the emerging TOP 500 list, the definitive global census of the most powerful computer systems. This work fostered a vital, synergistic relationship with LINPACK principal architects, most notably Jack Donder. The TOP 500 list's credibility depended on having reliable, verifiable data from all corners of the globe. Kanada's team provided it from Japan, offering more than raw performance numbers. They delivered results imbued with an implicit seal of verification. Their parallel work on pi served as an independent, long-duration validation of the hardware's fundamental arithmetic integrity. A machine certified by a successful multi-trillion-digit pi run was a machine whose floating point units could be trusted. This assurance gave Donder and the wider community immense confidence that the LINPACK performance figures reported by Kanada's group were accurate and meaningful. The influence flowed in both directions. By engaging deeply with the international standard, Kanada ensured his work and the machines he tested were legible and respected within the global HPC community. He was contributing to the creation of a shared scientific framework for assessing computational power. This collaborative process solidified a core ethos that Kanada's entire career embodied. Benchmarking is an exercise in establishing verifiable truth. The headline figure, whether measured in digits of pi or teraflops per second, was the end product of a rigorous scientific process rooted in numerical stability, algorithmic correctness, and a deep understanding of the underlying hardware. He demonstrated that the validation of a supercomputer was a discipline as demanding and sophisticated as the scientific inquiries the machine was built to perform. The quest for mathematical constants had evolved, yielding a methodology for certifying the very instruments of modern science. The establishment of a verifiable truth through computation became the central pillar of Yasumasa Kanada's intellectual edifice. His engagement with global benchmarking standards was the public-facing expression of a private, career-long obsession transforming the act of calculation from a mere procedure into a form of empirical science. The records he set for pi, while capturing the public imagination, were ultimately the spectacular byproducts of this deeper, more significant quest. The ultimate meaning of his career resides in the comprehensive methodology he forged, a systematic fusion of abstract mathematical theory, bespoke software engineering, and an intimate understanding of computer architecture. The celebrated numbers, stretching into the trillions of digits, serve as enduring monuments to this foundational contribution. Kanada came to embody the archetype of the modern computational scientist. For him, the computer was a laboratory, and the execution of an algorithm was an experiment. He operated in a domain where the correctness of a mathematical proof, the elegance of an algorithm, and the physical limitations of silicon were inseparable concerns. His work demonstrated that a sufficiently complex computation could itself be a source of new knowledge, revealing subtle interactions between theory and implementation. The development of his pi-calculating programs was an iterative process of discovery. A theoretical speed-up promised by an algorithm like the Fast Fourier Transform could be nullified by memory bandwidth bottlenecks or cache inefficiencies within a specific supercomputer architecture. His genius lay in navigating this treacherous interface. He would meticulously profile his code, identifying performance AOTS spots with the precision of a surgeon, and then rewrite assembly-level routines or even lobby hardware engineers for architectural modifications. This holistic approach, treating the entire system from the abstract formula down to the individual processor cycle as a single, coherent object of study, was revolutionary. He was proving the viability of a process, one where the pursuit of a mathematical constant served as the ultimate stress test for both human ingenuity and machine capability. His career represents the zenith of a particular epoch in computational history, the age of the monolithic supercomputer. This was a period defined by heroic efforts to extract the absolute maximum performance from a single, centralized, purpose-built machine. The Hitachi and later Hitachi supercomputers at the University of Tokyo were his primary instruments, and his relationship with them was profoundly symbiotic. He pushed them to their breaking points, and in doing so, provided invaluable feedback that drove the design of the next generation of Japanese high-performance computing hardware. This era stands in clear distinction to the contemporary landscape, which is largely characterized by massively distributed computing. Projects like the Great Internet Mersenne Prime Search or the collaborative pi calculations organized through Alexander Yi's Y-Cruncher software harness the power of thousands of commodity machines scattered across the globe. Kanada's world was one of centralized power, of a single mind wrestling with a single, colossal machine in a dedicated facility. His achievements are a testament to what was possible within that paradigm, a final, definitive statement on the limits of monolithic computation before the tide turned toward the distributed consensus of the Internet age. Yet, the obsolescence of his specific records and the hardware he used does little to diminish the enduring relevance of his core principles. The algorithmic foundations he helped to popularize and prove at unprecedented scale remain the bedrock of modern arbitrary-precision arithmetic. The reliance on variants of the Gauss legendary algorithm and the Salamin-Brent algorithm, both examples of arithmetic geometric mean methods, continues in contemporary record attempts. His pioneering use of fast Fourier transforms for performing the massive multiplications required by these algorithms is now standard practice. More profoundly, his unwavering commitment to computational verification established a gold standard that persists today. His insistence on calculating every record twice, using two fundamentally different algorithms, is a principle that has been inherited directly by his successors. Alexander Yi's Y-Cruncher, the dominant tool in the field today, has this verification feature built into its very core. A modern record is considered valid only after it has been confirmed, often using a formula from the Borwein brothers' family of algorithms to check a result obtained via Echelonowski's series algorithm. This practice is a direct intellectual inheritance from Kanada, a testament to his belief that a computed result without independent verification is a mere claim, a piece of data without scientific legitimacy. This influence on the subsequent generation is perhaps his most tangible legacy. Alexander Yi, the developer of Y-Cruncher, has explicitly acknowledged the foundational importance of Kanada's work. When he began his own journey into high-performance computation, he was able to build upon a wealth of knowledge that Kanada and his team had painstakingly generated and, crucially, publicly documented. Kanada's detailed technical reports describing the algorithms, the implementation challenges, the memory management strategies, and the verification procedures provided an invaluable roadmap. They illuminated the path, highlighting potential pitfalls and demonstrating proven solutions. Subsequent researchers were spared the need to rediscover these first principles. They could begin their work from a higher intellectual plateau. The lineage of modern computational tools for arbitrary precision, arithmetic traces its ancestry directly back to the methods that Kanada and his collaborators validated on the supercomputers of the 1980s and 1990s. He cultivated the ground so that others could plant new seeds. In the final analysis, Yasumasa Kanada's historical importance is secured by his role in transforming an esoteric, mathematical pastime into a rigorous scientific discipline. The quest for the digits of pi in his hands became a crucible for innovation across multiple fields. It drove the development of more powerful and reliable supercomputers. It stress-tested and refined a new class of powerful algorithms, and it established the foundational principles for verifying the results of complex, large-scale scientific computations. The final verdict on his career elevates him from a keeper of records to an architect of computational certainty. He demonstrated with irrefutable clarity that the journey toward a trillion decimal places was a process that forged the very tools, standards, and intellectual rigor that now underpin vast swaths of modern computational science. His work stands as a powerful affirmation that in the grand pursuit of knowledge, the methods we develop along the way are frequently more valuable than the destination we set out to reach. He sought a number, and in doing so, he helped to define an era.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.